Hi friends, Azi here. Today's discussion is all about Laplace transform. Laplace transform is one of the tools that is used in circuit theory so as to find a transfer function of equation to convert the differential equations into algebraic form for easily finding the solution of differential equations, etc. So let's start. See, basically, Laplace transform is defined by f of s is given by integral of 0 to infinity f of t e raised to minus st dt, where f of t is a signal as shown in the graph. The condition for that signal or the function is that it is to be defined at all points, and the value of f of t should be 0 when t is less than 0. Now, Laplace transform is just mapping the whole function f of t into another domain called S domain or complex frequency domain, wherein this function f of t is just turned into another function f of s, which is given by the relation here. You could see the function in S, which gives the integral of the f of t as shown. Because the f of t can be mapped into an S domain, there is a possibility that there exists an inverse Laplace transform, which is given by f of t is equal to 1 by 2 pi j integral minus sigma minus j omega to sigma plus j omega f of s e raised to st ds. The complex frequency domain is given as s is equal to sigma plus j omega, where the complete domain in S is just a complex frequency domain. It's not the frequency that we have dealt with in AC circuits. It's a complex variable. Now let's see the Laplace transform of a derivative of a function f of t as shown in the bracket. So if we convert the Laplace, take the Laplace transforms of a derivative of f of t, we will get Laplace of f dash of t is equal to s f of s minus f0, where the f0 means the value of the function when the time is 0, t equal to 0. So it is basically referred to as initial condition. Now let's see an example how we can apply this. We all know that voltage across an inductor is given by VL of t is equal to L di by dt. Now we apply the Laplace transform on the both sides. You could see VL of t turns to VL of s is equal to L into, and the Laplace of di by dt turned to be si of s minus I0. Usually the time domain current is denoted by small I, and the Laplace transformed current is shown by capital I of s. Okay, fine. Now if the derivatives is of order n, now say the Laplace transform of d raised to n f of t by dt raised to n is given by s raised to n f of s minus s raised to n minus 1 f of 0 minus s raised to n minus 2 f dash of 0, and it goes on until the numerator until the power of the s variable turns to be 0, that is 1. S raised to 0 is 1, and that function will be f raised to n minus 1 0. So the function, we are substituting 0 for the time variable in each function and taking derivative at each step, as you could see from the equation. That's the case when the derivative is of order n. Now, as we already studied derivative, there will be an integral form also. So if the integral form of a function is given by integral f of t dt, its Laplace transform is given by f of s by s plus 1 by s integral f of t dt at t equal to 0. So the initial condition over here is the second part of the equation. Now let's see how is it in network theory. Now the voltage of a capacitor, as you all know, that Vc of t is equal to 1 by c integral I dt. And when we take the Laplace transform, it turns out to be Vc of t. Laplace of Vc of t becomes Vc of s, and that is equal to 1 by c. Now Laplace of integral I dt comes to be I of s by s plus 1 by s integral I of 0 dt. Now suppose As we all discussed earlier, the nth order of differential, there will be multiple integral situation. If we take a Laplace transform of such function, the Laplace of nth integral of f of t is equal to f of s by s raised to n if the initial condition of the value of f of 0 is 0 in the case. So there won't be any initial condition. This transformation will be rarely used. Now, as we study circuit theory, we require a number of shortcuts or transformation of functions to be known. So here we are discussing a few transforms of function. These are standard signals or maybe some signals that we deal with. So I have listed out f of t as the time domain signals, and f of s is its s domain, its Laplace transform. So u of t is just step input. As we all know that the step input as we all know that at t equal to or greater than 0, the output voltage will be 1, that is unit step voltage, and if it has a magnitude of say E, then we denote it as E u of t. So the magnitude will be E and the value starts from t equal to 0. Now if we take Laplace transform of unit step function, we get 1 by s. So if it's a magnitude of E, then the constant will be retained back, and the Laplace transform of u of t will be 1 by s again, and E by s will be the complete transform of E u of t. Now let's see an exponential function e raised to minus alpha t. It's the function is defined like at t equal to 0, the function will be having value 1 and it exponentially reduces as the time increases, and the Laplace transform will be 1 by s plus alpha, and the function sin omega t will be transformed into omega by s square plus omega square. Cos omega t will be transformed into s by s square plus omega square. The function t raised to n, where n can have any real number value, will be transformed from n factorial by s raised to n plus 1. Then the function s sin h omega t will be transformed into omega by s square minus omega square. Earlier it was not a hypotenuse function, but this case it is a hypotenuse function which you should note down. So the other function is cos h omega t. It's transformed to s by s square minus omega square, and delta of t is transformed to 1. Delta of t is called unit impulse function, which is defined as when t equal to 0, the function will be having a value 1 of magnitude. It's just a single impulse function as shown in the graph, and taking the Laplace transform of delta t is just 1. So if it is 5 delta t, the graph will be turned out to be having a magnitude of 5, and taking the Laplace transform of 5 delta t gives a value magnitude 5. So that's all about just quick conversion of each functions. Now we have some special cases which will be helpful in network theory for finding the Laplace transform or its inverse. So one is time displacement theorem. If the function f of t is having a Laplace transform given by f of s, if we delay the function by a variable t, so the Laplace transform is changed by e raised minus st f of s. It will be much clearer with this example. See, we know the Laplace transform of sin omega t is omega by s square plus omega square. Now I applied an time delay with so now I am applying a time delay of alpha as shown, and the Laplace transform of sin omega t, which is given here, is multiplied by the factor e raised to minus alpha t, and this is how it is changed. So this is called time displacement theorem. Now second case, if the function Laplace of the function f of t is given by f of s, and if the time domain function is multiplied by e raised to minus alpha t, here we multiply it with s domain, Here we are multiplying it with time domain function. An exponential function is multiplied. So it turned out to be replacing its Laplace transform is easily obtained by replacing the variable s by s plus alpha. And we can discuss few examples based on this. Here on the right hand side we have three functions, sin omega t, cos omega t and t raised to n. The Laplace of each is already discussed earlier, which is omega by s square plus omega square, s by s plus s square plus omega square, and the Laplace of t raised to n is n factorial by s raised to n plus 1. Now, when the sin omega t is multiplied by a factor of e raised to minus alpha t, we replace all the terms in the Laplace s by s plus alpha. And this will be how, when we multiply each functions like cos omega t and e raised to n by a factor of e raised to minus alpha t, we replace all the variable s with s plus alpha as shown in the left hand side. So this will be another useful tool. See, if suppose we are having the equation and we have the equation in the right hand side of this equation, and we have to take the Laplace inverse, and you know the s square plus omega square is sin omega t, but the equation with u is s plus alpha whole square plus omega square. So this s plus alpha will be converted to e raised to minus alpha t times sin omega t, and we know the Laplace inverse of sin omega t, the other function. If you multiply e raised to minus alpha t, it turns out to be e raised to minus alpha t and Laplace inverse of omega by s square plus omega square, and you be knowing naturally the inverse of omega by s square plus omega square is sin omega t. Make note of this point, this is very important and will be very helpful when you study. Now we are going to discuss about initial value theorem. What is initial value theorem is all about? See, if suppose you have a capacitor that is connected to a circuit, you want to know what is the current flowing through the circuit at the point when the capacitor is disconnected. So it's at the time instant t equal to 0, just connected. Or suppose if there is an RL circuit and you are connecting a voltage source into it, you want to find what is its starting current when just the circuit is connected and what will be its final current. So for that, for finding the starting current, we will use the initial value theorem, and for finding the final current we go for final value theorem. Let's go into it. So if the current is given by some function f of t, and the value of f of t at 0 plus is given as, in Laplace transform, we multiply the equation of the current in Laplace with s and apply the limit s tends to infinity. That's how we will get the value of function at t equal to 0. And that's all about initial value theorem. And you will be discussing few examples related to it, and it will be much clearer. Now final value theorem, as I already stated, you want to find the current in RL circuit or when t is equal to infinity. So when the system has attained a steady state, that state is called steady state, and the moment the system has attained steady state, we have to find value of what is the value of the current. So if suppose I express the current in function of f of t, now I have to find value of t at infinity, and in s domain it is fine. Suppose if we have the equation in s domain, just multiply with s and apply the limit s is equal to 0, s tends to 0, and you will obtain the value of that function f of t when t equal to infinity. That's all about final value theorem. So initial value theorem and final value theorem are easy way to determine the value of the function in time domain when you have the function in s domain. Okay, now let's go for the convolution. See, suppose there are two functions, we have f1 and f2. So multiplying both function, when the convolution is all about taking f1 of t multiplying with f2 of t. So the operation is called convolution. the whole operation will be known as convolution. And what actually happened is that the function f1 is convoluted over f2. The simplicity of Laplace transform here is that, see, why we can't multiply both functions f1 of t and f2 of t is that there will be value for each instant t1 of f1 as well as f2. See, so at each instant we should multiply. So that whole process is called convolution. And if we take the Laplace transform of the both function, we could just straight away multiply, take the product of the both function f1 of s and f2 of s, and that is so simplified form, that is so simple form that we could make up, and finding the Laplace inverse will just give the straight away result of f1 of t convoluted over f2 of t. So that's one of the application of Laplace transform. Now till now we discussed all about Laplace transform. Now let's discuss about inverse Laplace transform. See, for that we will be getting see we know how an equation, what will be the inverse of simple terms like 1 by s plus a or a by s plus a, or 1 by, as we already discussed, say omega by square minus omega square s square plus omega square, which will be sin omega t or sin h omega t, etc. So once we have some current equation or voltage equation, it won't be as in the form as we desire, like in a symbol form. So it will be a complex term with a higher order of s. So first of all we should convert into a symbol terms, like a product, the denominator will be converted into symbol terms of possible order as like shown in the figure, and we have few forms, and we will be splitting the whole equation into simpler terms by the method of partial fraction. Now let's discuss a few techniques how we are finding the partial fraction from a complex term like this in the left hand side. So here we have two symbol roots, s plus a and s plus b. Initially it will be a product, it will be a square plus 2 a plus b into s plus ab, maybe you will be arriving at this equation. If you could find two real roots for the equation, then split the equation as in the form of roots s plus a and s plus b, and by partial fraction method you could rewrite the whole term as a by s plus a plus b by s plus b, where a and b are real roots, and we have to find what will be the value of a and b by some techniques, maybe Heaviside method or cross multiplication technique. We will be discussing one technique in this lecture. Next, the other form is ps plus q by s plus a all raised to n. Here p, q, a, b, etc. will be simply constants, and s is the only variable. So when there is a term at the denominator with power n, we should split into n terms like this, where it starts from the power 1 to n and having a term at the numerator a, b, etc. So ps plus q by s plus a all raised to n can be written as a by s plus a plus b by s plus a all square, etc. plus n by s plus a all raised to n, where a, b, etc. n is a real number. So this is another form having nth order for the denominator term. So you will be getting a combination of the above term s plus a into s plus b all square maybe, or cube maybe. So you should have a combination of this first term and few terms from the lower form. So these are the most possible form you could obtain while doing partial fraction. That's we are discussing right now. Now other form is p square plus qs plus t by s plus a by into s square plus as plus b, and this can be, we know there is a single term over here, so we are splitting it in partial fraction a by s plus a, plus the second term. The speciality of this term is you couldn't write this in the form of s plus a into s plus b because it doesn't have a real root or a complex root. So in that case we will be splitting the term as bs plus c by s square plus as plus b, where a, b, c again are real numbers. So we can write this alone in this way alone. and we should find the value of a, b, c, etc. Now other form is ps plus q by s plus a into s square plus b square. So this term is a complex root and we can split like this. This is similar to the first form and we can split into three terms having similar order of one equation. And the specialty over here is that always be the numerator of the term s plus jb, and the numerator of s minus jb will be complex conjugate.